Swayam Prabha. Digital India. Educated India.
Yeah, good morning everyone. So I am Arnab. I'm going to chair this session. So at the first, I would like to introduce Professor Dominic. He's from University of Nottingham, Malaysia. So his talk today will be on process integration, systematic tools for resource conservation and beyond. So Prof. Dominic is a professor of process design and integration at the University of Nottingham, Malaysia campus. He's also the founding director for the Center of Excellence for Green Technology. He's a fellow of Institution of Chemical Engineers, fellow of Academy of Science Malaysia, and various other academic bodies. He's also among the top 2% of the world leading researchers working in process integration for resource conservation and CO2 reduction. He has several publications and book chapters in this area. So the floor is yours, Prof. Dominic.
Thanks, Chairperson. I have 40 minutes for this beacon talk. I'll give you an overview about process integration. Many people know this as an energy saving tool, but today we use it for various other options or debottlenecking or optimization framework. Okay, I'll give you an overview. In process integration, we have heat recovery, material recovery, and nowadays we talk about production planning and CO2 reduction. But due to time constraint, I can only give you a very short overview on each of these particular topics over here. In the first place, this is a tool that we always say is that serve as a quick kill solution because we are looking for something fast, something that wouldn't take too much time to develop. Because in industrial practices, we simply don't have time. You talk to any industry guys out there, they'll tell you, if possible, I want a solution by yesterday. Okay? Forget about asking them to sponsor a project which is 3 years for a PhD, if you're talking about a solution of yesterday. So my research team, my collaborators and I always try to get something that is quick kill, okay? Something that you can use immediately without much efforts to write the codes and all those things. Of course, you want to do some Python's optimization, it's fine, but we get our PhD students to do it. But if you want to do it something yourself, okay, we always introduce something which is graphical in nature. In the first place, processes, chemical engineering domain or chemical processes always can be described in two main elements, the mass perspective as well as the energy perspective. When we talk about the mass perspective, we talk about the conversion of feedstock or raw material into products and byproducts. If we can make the best use of products and byproducts, we can maximize the product and byproducts. That maximizes our profits, and at the same time, it minimizes the effluents and spent materials. So that's the mass perspective. At the same time, we also have the energy perspective where we make the best of energy resources, be it hot utilities, cold utilities, pressure pumps. All this can be something that will help us to save operating costs, and that get us a higher profits. So for this particular area of research, been there for the past 4+ decades. Okay, back in 1970s, a lot of works were dedicated for the synthesis of heat exchange network due to the first oil crisis, and then it ventured into various options to maximize energy saving. And late 1990s, we see 1980s. Sorry, we see the extension into mass recovery, or in specific, the first one was mass exchange network. Mid of 1990s, we see the extension into some special cases where we talk about recovery of water, utility gases like hydrogen. Later on in the new century, we see property integration. Lately, the last decade, we see a lot of work on CO2 reduction. I should sort of tell you that these main techniques of process integration have two big categories of family. Back then in the 1970s, these are enemies. Okay, you go to any conferences, they will talk bad about each other. Okay, nowadays we understand that each of these domain has its own pro and cons. It has its merits, it has its disadvantages. We just have to make use of the right methods for addressing certain particular area of that we're trying to resolve. Okay, of course, when we talk about graphical methods or insight-based methods, the most popular methods is even in the textbook is pinch analysis. And at the same time, we have also the magnetic programming methods that many works have been published. And this tool nowadays is coming into something called hybrid techniques, where you can actually formulate something which is insight-based into optimization, or the optimization can also take the insights from insight-based techniques, and so on and so forth, to address problems that can't be done individually. Okay, let me first kickstart with this heat recovery system. I believe many have learned something called heat pinch analysis. Okay, for the benefits of those who are new, we talk about the recovery of energy from hot streams into cold streams. When we talk about hot streams, those are streams of high temperature. We're trying to cool down to low temperature. If we don't recover the energy, we just have to discharge, or well, in a way, remove the energy using cooling water or chill water, etc. Now, at the same time, we have cold streams. Okay, cold streams are streams to be heated. Things from low temperature to high temperature is cold streams. Hot temperature to low temperature, high temperature to low temperature is hot streams. So when you have hot streams, we plot a hot composite curve. Okay, when you have cold stream, we plot a cold composite curve. The overlapping regions tell us how much energy we can recover. For this particular example, the values here for energy recovery is 51. In order to achieve this, we need to place the hot composite curve by a small delta T mean of 10 Celsius or 20 or 30, depending on where the plant is located. And whatever extension on the right-hand side is the minimum hot utility needed. Okay, for this particular case is 7.5. Cold utility needed for this particular case is 10 megawatt. This has been a very established method for 40 years. Okay, you open up any textbook in chemical engineering design, you find at least a chapter. Okay, whether you like it or not, it's there. Some people don't believe it, but it's there. Okay, these are textbook material. Why is it textbook material? Because it's systematic method. Everybody do it, get the same answer. Okay, prior to the introduction of this systematic method, many other heat recovery so-called methodology have been developed. However, the method is not systematic, so different people do it, get a different solution. This has been addressed using pinch 40 years ago. Okay, so that's the term here. Pinch is actually representing the closest delta T log mean. Okay, the minimum driving force. That's the driving force for heat recovery, and that's the name where it's so popular. Everybody known this as pinch. Okay, but like I told you, process integration has two big family. Apart from pinch, there's also mathematical programming. Okay, so when we have the energy recovery pinch diagram being drawn, what we need to do next is to make sure that targets get achieved. Okay, using another diagram, we call this a grid diagram. You pair the hot stream with a cold stream, placing the heat exchanger represented by the bicycle with a vertical line. This is each of these is a heat exchanger. The moment you convert it back to process flow diagram, you can see that energy is being recovered through the hot and the cold streams through this heat exchanger in the plant. Okay, anything that we need further heating, for example, this 7.5 is taken up by the heater. Anything that needs further cooling by the cooler, that's taken up by the cooling utilities exchanger, and that target has been identified in the first place using first principle. So in the classrooms, we do all this teaching to tell students that, look, if you can plot a pinch diagram, your grid diagram should match the target that you establish using a pinch diagram. If you don't get the results exactly the same, either you plot the pinch graph wrongly or you design the heat exchanger network wrongly. Okay, these are very established. Okay, so many people cover this in the classroom. Now, something that a lot of universities do not cover is this utility selection, all right, or utility optimization. Well, why? Because not enough time. Okay, but so you can actually ask your students to do it themselves. I guess by plotting this grand composite curve, which actually optimize the use of steam. Okay, there are high pressure steam, low pressure steam, medium pressure steam, hot oil, furnace. All these are hot utilities that we can optimize. The key is to make use of lowest temperature hot utility possible, because that is cheapest. Okay, anything that higher temperature is going to be expensive. Below the pinch, we have the cooling utilities. If possible, we want to use the highest temperature cold utility, because that is cooling water. And it depends on where the plant is located. If you are building it in Chennai, probably the cooling water temperature is about 40 Celsius. If you're building this in UK, this is a cooling temperature of maybe 15 or 20 Celsius. So please be aware to alert your students. Don't just take the textbook value. A lot of students just take the textbook say 20 Celsius. I'll put a cooling water of 20 Celsius. It certainly will not work in most plants in Asia, at least in the South Asia. Okay, I come from Southeast Asia. The moment my student says my cooling water is 20 Celsius, everybody plant in UK, no, please make sure go and check what is our air temperature out there. So this is something that practical that we need to train our students to understand. Please use your engineering mindset. Don't just go with a textbook. Okay, because a lot of textbooks are written by authors from temperate country. Okay, all right. Let me draw your attention also. Apart from utility selection, nowadays we are going into a lot of new domains. One of those is cogen. Cogeneration is always good because it maximizes the energy resources. In the first place, cogen is not new in pinch. Okay, some of the early experts of process integration have addressed this in as early as 1990s. Okay, in recent years, a lot of industrial practices are looking into the best use of combustible waste. This waste that they are conventionally dumping off-site, okay, sending to some contractors where they will be using it to off-site treatment, landfill or incineration. Nowadays, a lot of industry are trying to make use of these energy resources. I should say combustible waste as energy resources. In the first place, you minimize the waste, you minimize the cost of sending your waste product for landfill. At the same time, you can make use of that to generate power and steam for your plant. So if you do cogeneration, especially using combustible waste, it addresses problem for minimizing the waste, converting the waste into energy. So it's a waste to energy problem. Some of the methods developed in the recent years, that includes, so if you're doing the cogen targeting, okay, this is another pinch diagram for cogen targeting. You can see that we plot the steam demand and steam sources. When you have the usage of steam in the plant, and then there will be ways that you can generate steam. This is the steam sources are the things that you can convert from your combustible waste. Steam demand are all the energy needed in the plant where you need to provide heating using high pressure steam, medium pressure steam. What you need to do is to, okay, so what we do is the moment we plot this pinch diagram, the composite curve can tell you how much the cogeneration potential we can generate using the waste. Okay, and as I told you, you can combust the waste. It will be able to generate power, steam. At the same time, you reduce the dependency on external fossil fuel, external power producer. Okay, so that you can also even consider whether the excess steam can be sold to the neighbor plants, etc. Okay, so with that, you can derive the cogen diagram on the right hand side, where you can see that the different level of steam are used. For example, this is the very high pressure steam. You generate power that led down to medium pressure, and there's a HP steam that you generate led down to medium pressure. This high pressure led down to low pressure. So everything can be derived from the pinch diagram. This is not too new. I would say about a decade old. Okay, getting more popular, and a lot of industry are picking up because they want to convert the waste into energy. All right, can skip this. We just need to ensure that the high pressure steam must always be higher than the low pressure steam. Okay, that's the diagram that we can generate. Okay, I won't go to the details if you are due to time constraint. If you are keen take a look on some of these books. These are those common books in the markets that you can find some of the good material about energy perspective of process integration. Apart from CoreGen, there are also a lot of work done by various authors on heat engine, heat pumps, heat integrated distillation columns, dryer heaters, anything to do with heat integrated equipments. I would say 70 to 80% of those material are already in textbook, meaning that you can use that for teaching. You can use that for solving industrial problems. If the students are doing some design project, ask them to explore some of those advanced topics in the textbook. Okay, those are all available in the market. Now, some of the statistics shown by some Canadian survey. Energy saving is always good. I usually tell my students, if you can save 5% of energy, this is a good bonus for you next year. Okay, tell your boss, I just want 1%. You know, that's my bonus for next year. Still a lot of works are still ongoing in this particular area of research, even though some people say that, oh, this is already a sunset research. Well, yes, if you're just looking into heat exchanger network itself, yeah, it's kind of saturated. But the recent years, I still notice that there are still quite a lot of works done on retrofit. Retrofit means that you go to the plant, heat exchanger already there, heat recovery have already taken place. However, they are not optimized. They were done based on some ad hoc decision. Why are they pairing the outlet stream for a reactor with the inlet stream? Or because they are nearest. Okay, pairing that does not mean they give you the best energy recovery. So if you want to do retrofit, you're going to identify the cross pinch matches, trying to modify them, trying to add more shells to your heat exchangers, trying to improve the heat recovery. All these things are called retrofit. Okay, the conventional textbook pinch method may not get you the best solution because those assume nothing is built. On drawing, we have the PFD, we simulated the files and the process, and then we do the pairing. The moment you step in the plant, a lot of these plants have been operated for the last 30 years or 50 years. Those were plants that were not designed systematically. Okay, they were not designed systematically. The moment you step in and do retrofit, this is a whole lot of problems, headache that you have to address. Okay, identify the cross pinches matches are also a big headache. Okay, and also I noticed that a lot of research were done on incorporating renewable into energy recovery. Lately, several papers have came into this new area called electrification. Instead of using fossil fuel, okay, you need to understand that our chemical industry are actually consuming near to 1/3. Okay, 30%, 28% of industrial energy is consumed by the chemical industry, and big majority, 95% of this are from fossil fuel. Okay, so what we noticed lately, there are some researchers done some work to replace the conventional fossil fuel kind of a domain using renewable energy or anything that is coming from non-fossil fuel resources. Okay, for example, this was the grand composite curve that I shown you just now. Okay, instead of using furnace steam, now you can replace the steam using electrode boiler, and this one is by electric heater. And these are ongoing research that I've noticed some people have published this. Okay, if you're keen, do a search, less than 5 papers in this area. So if you're keen to work into it, this is a good area of exploration. Okay, so that's the main things that I want to draw your attention in heat recovery. Let me go into material recovery. This was something that I've been doing since my PhD time for the last 20 years. In the first place, these are the strategies that we make use for material recovery. Okay, it goes from reuse, recycle. Reuse means that the waste from one unit goes to another unit. Okay, recycle means that it goes back to the same unit. That's called recycle. Some cases we do not tolerate recycling because there could be accumulation of impurity. Maybe that particular impurity they're looking at is not accumulating, but there are other materials that is accumulated in the system. So we try to avoid that in some processes. Let me just show you if I have a unit, okay, that consume resource and a unit that produce waste. The inlets where the unit is consuming the resource is known as sink. Okay, this is a sink where it can be water sink, hydrogen sink, solvent sink, solid sink. Anything that consumes a resource is known as a sink. Anything that produces a waste which you want to consider for recycling is a source. When you have a sink, you have a source. The challenge is to identify how can we pair the sink and the source. Of course, when you only have one wastewater and one unit that require water, you know where you send to. The problem is not that straightforward. In some refineries, you have 4 or 5 sinks units that require water, and sometimes you have 10 wastewater streams. How to systematically pair them, okay? Parallel to the introduction of water pinch, various people have done water recycling. Of course, in the industry, in the academic world, many people have done water recycling studies, but not systematically, okay? When I mention systematically means that you, I, your students, everybody do it, get the same answer. Nobody can get a better answer because that's really the best answer, okay? So when you are talking water recovery in the process plant, a lot of the time processes utilize water once through. The moment they utilize, send it to wastewater. Why don't they consider recycling back then? Water is cheap, okay? In countries like India, like my country, Malaysia, you put a pill outside, tomorrow you get this much of water. Why we bother about recycling? But nowadays, people are alert that water is a precious resource. Many countries have lacking of water for use, okay? And sustainability aspect come into picture. Back then, 20, 30 years ago, when you talked about water saving, you said, don't waste your time, okay? The money that you save is too little to be significant. Nowadays, they say, oh, don't talk about water, we talk about sustainability, okay? Talk about how to make our company greener, all right? What we need to do is to identify water sinks and water sources. Okay, for example, this is a very simple case study where water are utilized in those 2 units. These are water sinks. And then most industrial practitioners or non-PSE researcher, okay, you usually take this water source. Okay, you have wastewater, I'll take this, channel it through my membrane or channel it to my filter, and I'll recycle back to here. Depending on how much water you have, the entire wastewater will be treated and up to drinking water quality, send back to your processors. But fine, this is a solution. They'll tell you that I'll offer you the best solution. You give me the contract, I'll serve you for 10 years. I'll give you the best membrane under the sun, and every 3 months I come to backwash, and every 2 years I will change the membrane for you. That's how they do the job. We as a systematic persons, okay, process system engineering researcher feels that this is not the best practice, because if I can identify the individual wastewater, you will know that certain water are clean, certain water are not as clean. The moment you mix everything together, you say that they are diluted. The dirty one becomes slightly cleaner, but the clean one becomes dirtier. Okay, if you look at this particular problem, we are looking at the contaminant of ammonia. This contamination here, ammonia content is 20 ppm. You look at this individual wastewater, this is 0, this is 14. Both are cleaner than this. If you talk about potential for recycling, these 2 are much better candidates for recycling. Of course, it gets diluted because it's 25, there's 34 ppm. So the best things to do here is to get them segregated, and then before you can perform a water recycling study. The moment you go to the plant, then you realize that this is not as straightforward, because they say that we monitor the wastewater, but we do not monitor the individual wastewater. So what we need to do is do some backtracking, do some simple testing, take a stopwatch and put a pail there and measure how much water is being produced every moment, do a test for a few days, and that get you the flow rates, and then you can do the testing from, you can do the analysis from there. Now, the moment you collected the flow rates and the concentration, then you can next move on to look at how can we analyze the problem. If you are looking at a single contaminant problem, usually we'll just do it using pinch. If you are doing more than single contaminant, don't have time with pinch, okay? There's mathematical programming where you can code everything using a spreadsheet, and or even some programming, high level programming, which you can do that, okay? But for this particular simple case study, I can tell you, more than 60–70% of industrial problems are single contaminant. Or you can say that, well, we have suspended solid, we have COD. Yeah, but suspended solid can be correlated with COD and can be treated still as single contaminant. Because if you reduce suspended solid, COD content will reduce. Okay. Of course, when you are talking about suspended solid and iron content, sorry, these are not correlated. This is no longer pinch domain. This is mathematical programming. Okay. So address the problem using the right techniques. If I would plot this particular single contaminant problem using a water pinch diagram, it looks like this. The blue line indicates the 2 units that consume water, which is the boiler feed water and scrubble. That 4 wastewater at the bottom of the tables are the 4 individual wastewater that you want to consider for recycling. The moment you plot it out, this is the source composite curve. This is the sink composite curve. We need to ensure the source composite curve is lying on the right-hand side and below the zinc composite curve. In this case, zinc composite curve, vertical distance of that zinc composite curve, telling you that you do not fit more than 58 milligram per second of impurity. For this case, ammonia content. Okay. The moment I shift the source composite curve to the right-hand side, I will blend it with fresh water, and this is the point where they are touching. At this point, you notice that the impurity are building up to 58. Okay, so this pinch is stopping you from doing more recycling. Okay, and the overlapping regions here tell us how much water can we recover, 4.9. Whatever remaining, these are wastewater that should be discharged. Okay, when you say discharge, means that you will send to waste treatment plant and then treat for environmental discharge. Usually, the moment you carry out water recycling, the impurity will shoot up. We need to ensure that the waste treatment plant can cater the higher level of impurity. Okay, doing that help you to reduce fresh water, wastewater, water costs, chemical costs. In some cases, for this particular case, improve productivity. This particular case, the main problem was the wastewater treatment facility is already at hydraulic bottleneck. If you can remove the hydraulic bottleneck, they can produce more products, and that help you to improve profit. So this is one stone for several birds. Okay, freshwater, wastewater, chemical costs, and higher profit. Okay, and of course, some cases, if you do reuse recycle, they only give you 5%, 10% of water saving. You may want to address a bit more by putting in extra unit. For example, if you put a filter or a reverse osmosis unit, that can help to improve the quality of waste before you recycle them. Okay. Technically, if we do it in mathematical programming, we'll draw a superstructure like this. Okay, and the model will tell you which of these pipeline contain a flow rates, which of them is 0. And graphically, you say that, oh, this is the wastewater going out. I take a portion of this, send it back for purification, and it will reduce the fresh, can be fresh water, can be fresh hydrogen. Okay, the thing is, this optimization variable is fresh water as well as the amount of flow rate that you want to pass through the filter. So one of the options that you can do is set up some model. Okay, the good news is the last decades or so, our computational software, including Excel spreadsheet, you have the optimization toolbox of Solver, the advances in process integration with the development of a lot of linear problem, allowing Excel to be used to do this kind of optimization. This is a paper that I published in Chemical Engineering Progress, teaching engineers how to make use of spreadsheet to do water pinch. Okay, you can also do the same thing for mathematical programming. So if you do this for this particular case study, you can put an absorption column there that help you to reduce water. You can also get rid of the steam injector, and that help you to eliminate one water usage. Okay, and then the final solution that I implemented in the plant is to replace the vacuum pump, put an absorption, then you can recycle. In a nutshell, when we say systematic method, this address water recycling. For this particular case, water recycling problem from several perspectives. We always look at how much are we using for base case. Then we explore, reuse, recycle. This is the low-hanging fruits with the minimum cost. If you have more money to spend, then we put in regeneration unit. Can be a filter, reverse osmosis, distillation, absorption, ion exchange, you name it. You can evaluate different regeneration unit using this. Okay. You can also address process changes. The option is that you go up the hierarchy, you're going to spend more money. Okay, the lowest expenditure is always reuse, recycle, which your workshop people can do the job. If you want to invest in regeneration, you need to have some capital costs. If you're going to do technology changes, like replacing the vacuum pump, you need to modify the processes. There are a lot more things, complications that come in. So we always go from the lowest hanging fruit, tap the lowest hanging fruit before we explore the more complicated options. Okay, so acceptability always moving downwards is the best. Okay, costs going up, okay, it's higher. Okay, so there are this survey done in Canada saying that water saving can be 25 to 40% for these refineries, pulp and paper, chemicals. Some of these industries really consume a lot of water. All right, the same concept if I can do for water, I can do for hydrogen. The only difference is you take the O oxygen out from water and that becomes hydrogen, isn't it? So the same concept can be done if you have a lot of hydrocracker in the refinery. We explore the usage of hydrogen resources. You can see this diagram is moving to the right-hand side. That's where the pinch and the overlapping region tell us how much hydrogen can be recycled. Exactly the same concept like water. So I won't go to the details. The moment you can recycle some hydrogen in the plant, on paper, it looks simple. The moment you want to implement it, there will be pressure constraint that you need to address. There will be sometimes some impurity constraint you need to address. So implementation-wise, it's more complicated compared to water. Okay, of course, if you are doing using optimization framework, this can be addressed. Okay, you can also take a look. Some of those papers published by various researchers. Nowadays, a lot of hydrogen integration, hydrogen optimization work was done in China. Okay, because they have a policy to optimize the plant every 3 years. So it's a good initiative. Okay, the typical saving reported by Canada, you can see that hydrogen demand will reduce up to 20%. OPEX, CAPEX get reduced. Okay, I should quickly show you some variants. In the last couple of slides, I show you water, hydrogen. All these are mass integration or mass recovery perspective. Things get more complicated when you're trying to handle batch. Okay, when you are going into polymer industry, food industry, yeah, in batch operation. Your wastewater is available sometimes. Your units that require water is only sometimes. So you need to address them by putting a storage tank. Okay, the case become more complicated when your plants are huge. Okay, if you are trying to pull a pipeline across the beginning until the end of the plant for 2 kilometers, this is impractical. Okay, the amounts of water that you save may not be even enough for you to run the pump. Okay, so in that case, sometimes you want to segregate the plants into different sections, do some integration among these sections before you explore the wastewater to different sections. You will still get some water saving, not as best as you treat them as an overall. But from practical viewpoint, this at least get things going rather than pulling small little flow rates that the pump can't even run. You understand what I'm trying to say, right? So things are like, for example, you can have one network by itself. These are 2 different networks. We explore the internal reuse recycle before we export the flow rates to another plant. Okay, these are some of the references you can find on the market. Of course, being a salesman, I will tell you the first one is the best. Okay, that's because that's my product. Okay, now of course you can also look at some encyclopedia chapters and some light reading materials. These are all in magazines. I publish more papers in some papers in magazine nowadays because I run that this technology should not be just limited to our academic community. Industry people out there, very rarely they will read our journal papers. So fellow researchers, if you think that your work is already established, don't just publish in journals. Go out to magazine and publish there. You will get a lot of nice feedback from the magazine readers. I want to implement your techniques in my plant. So can you help me? You get all this feedback. All right. Some of the ongoing research in mass integration, people are trying to look into energy-water nexus. This is one option. Some of the works done in heat integrated water networks is also ongoing. Okay, I won't have time to go through the details. Finally, let me just draw your attention a few minutes for this beyond resource conservation. Chemical engineering, we talk about mass energy resources. Okay, outside chemical engineering, a lot of people are still using pinch. Okay, using process integration, using mathematical programming to address production resources. One of these best thing that we need to do is to how to optimize financial resources. Okay, you have money. You have projects that need money. This is another sink source problem. Any companies will have some financial resources, and all companies are looking into projects, how to do improvement. And for example, in this case, I have 6 projects I want to implement. Each of them requires some investment. Again, each of them have some typical saving. You will have some money from the HQ. HQ say if you need more money, go to the bank. The bank will say that you need to have some kind of a payback period or some kind of interest rate. Okay, obviously the interest rate will be higher than what you can encounter from internal grant. So how to make the best use of this is to look at how the payback period or the interest rate. This diagram is the core financial pinch diagram. We plot the 6 projects according to its intensity. This intensity is expected payback period. The shortest payback should be optimized. It should be prioritized first. The longest payback, put it later. Okay, that's why you see the diagram is shooting up like this. Anything on the right-hand side shortest payback. Anything on the left-hand side is the longest payback. So when you have your financial resources, and it's always limited, okay, you only have this amount of money. So if you want to make the financial resources, need to make sure that it's on the right-hand side so that you will be investing for this particular case, project 3, 4, 5, 6. These two, we probably have to abandon until we get the big pocket who will invest with us. Okay, this is financial resources. You can do the same analogy to do, nowadays a lot of companies are looking into CO2 footprint reduction. If you implement CO2 footprint reduction, also needs money. And most of the time money is always limited. Okay, how do we prioritize that? We try to look at the reduction intensity. Anything that has a high reduction intensity on the right-hand side, on the left-hand side is low reduction intensity, meaning that every dollar and cents that you invest, every rupees that you invest, you want the best CO2 reduction. Okay, this is something that we plot CO2 reduction on the y-axis, a money financial on the x-axis. Okay, if you are keen to take a look, I can send you the paper. Okay, finally, let me also show you, apart from money, you also look at how can we optimize human resources. Okay, a very simple example, if you ask the whole class, ask them to plot out their Gantt chart when they need to deliver coursework or assignment, they will usually tell you the pinch point is the day before the submission. Okay, and this is the problem, a very common problem. You do the same thing for consulting company, a few engineers working in the same projects, and this is, they have to deliver these tasks, and these are the time they have. The moment you shift them, the composite curve, that's the pinch diagram. Okay, this is where the pinch is located. This is the day that you will run out into trouble. So when you want to do this, that helps us to, what you can do is to plot the grand composite curve so that the planning can come into picture. These are engineer 1 to support engineer 2. When you do a big project, usually you have several engineers in the team. Engineer 1, they will have some free time after the pinch day. Okay, engineer 2, if he has a pinch day later, you can get engineer 1 to help the engineer 2 because this guy will have some free days here. Okay, and this guy need help over here. Okay, this is how you can plot the grand composite curve to look at planning for resources. And you can do this for consulting company, usually consulting company with several engineers. And this is another optimization framework. We optimize concept based on pinch. So for instance, in this case, 4 engineers with the same skill. If these 4 engineers cannot fulfill the job, you need to hire external person. Engineer, a worker 5 and worker 6 are someone that you will hire from another team. They are multi-talented workers which can do things faster, but we want to minimize them because you need to pay your another team for external resources. So you can optimize this just like what you did for heat pinch, financial pinch, it works the same way. Okay, so I will also show you, this is the resources for production. So I won't have time to go to the details, but let me just conclude that anything that you can address using process integration is based on quantity and quality. If you can identify the quality, for example, human resource is time. Quantity is also time, the duration that you have. Time is a date where the deadline comes from. So you can address this. This will be able to address many, many problems. Okay. Finally, let me acknowledge all these collaborators been developing all these fancy ongoing process integration research. Okay, some of them are here with us. Okay. Right. Thanks very much. If you have any questions, we can take one short one.
Yeah. Thank you. Yeah. Can we have some quick question from Prof. Dominic? It was a nice, insightful talk on process integration. Yeah.
Yeah, no, thanks, Dominic. That was a very good presentation. I just want to find out, you did not say much about the possibilities of a hybrid space or net framework where we use both graphical techniques and mathematical techniques. You mentioned the mathematical techniques in isolation of the graphical techniques. Do you think there's an avenue? And maybe if you can share with us some of the experiences, what can we perhaps achieve by using both graphical and mathematical together?
Thanks, Professor Chokoma Georgie. I will ask the questions about this. Sorry, I don't have too much time for that. This was actually the optimization framework. The concept was based on pinch. Okay, and those of you who know heat pinch, you know that this is grand composite curve. You can construct the grand composite curve using problem table algorithm. If we do the same thing for human resource or any other resource conservation, this is the source, this is a sink. We set up at every level, okay? And if you have a resource, is a source, this is a sink. Anything that at this level can be utilized, anything that is left over go to the level down there, okay? Now, when we coded this in optimization framework, you notice that all these are omega, these are all variables, okay? These are all variables. What I did was I minimized external resources, which is worker 5 and worker 6. My optimization framework will tell me how many worker days worker 5 will have to come in, how many worker days this worker 6 have to come in order to minimize the workers by minimizing their salary. Okay, their salary is higher compared to the 4 workers working in the project. Okay, your project team have 4 workers. These are something that we're already paying using that particular team budget, but worker 5 and worker 6 are someone that you borrow from outside. Okay, so we minimize the cost for worker 5, worker 6, and that will give you the optimization results. Yeah, and this is the same concept that we use for water, hydrogen, property integration, cogen. Okay, you can just set up a spreadsheet like this and optimize the cost for that. Yeah, I hope I answered that.
Fauzi from Malaysia. I would like to ask, since you study a different scope like energy, water, is there any like interaction between those, let's say, for example, energy and water, then you put it in pinch together? I mean, simultaneously effect, or what's your opinion?
That is also another example for hybrid method, because this technique is inherently addressing only 2 dimensions. You can only do either water or energy if you do purely graphical method. For example, something like this. You can either draw impurity, this is flow rate. You can't draw energy. So when we're addressing things like heat integrated water network, you cannot just rely on diagram itself. We have to use optimization framework. For example, this one. Apart from water, you have hot utility, cold utility. So what we did was take the pinch concept for heat recovery and take the mathematic programming methods for water recovery. We construct a network where water can be recycled from the sink, from the source to the sink, and every recycling is an option for heat recovery. So the heat recovery is done using pinch, the water recovery is using mathematics. So this is another example where you marry the 2 methods, and we can't solve it using graphical. We have to solve it using optimization framework. Yeah. All right. Yeah. If you are keen, and this was done using Excel spreadsheet, as simple as Excel spreadsheet. Reason why Excel, because it's LP, linear program. I have a spreadsheet tool that I can just click. It's 10 Celsius, 20 Celsius, 30 Celsius, 40 Celsius, and it's in spreadsheet. Because the moment you show the industry people, they say, "Oh, this is too complicated." You show them Excel spreadsheet. "Oh, this is easy." Yeah, that's easy. Yeah, it's actually easy. If you know how to convert the thing into a linear program, Excel will work for fine.